Okay, so welcome all to this session about building interactive networks in Observable using D3.js. In this session, we will be talking about how to build an interactive networks using some data that we will collect from the network, from the internet. We will then process it in a Python notebook. We will analyze it. We will understand what data we have there. We will understand which relationship we have there, and then based on that, we will build a data file that we will upload in the net, and then we will use this data file to construct an interactive network and visualize the different relationships that are in this file. Let me start introducing myself. I'm Arnau Quinquillà. I'm currently working at Sirius Academic as an analyst, and a consultant, but I have been working as a data analyst and also as a web developer, creating several data visualizations. And some years ago, like around five years ago, we were working with Albert Diaz in two projects. One of them was in visualizing the co-authorship between researchers in Universitat de Barcelona, but also we did a project in visualizing the collaborations between actors in the domain of complex networks. So before going on, I would like to thank Albert Diaz for the opportunity of giving today this session. So let's start from the beginning. We will talk now about wide networks, but before doing that, I would like to point out two things. The first one is that you should have at this moment access to this observable notebook that I'm showing to you, which is one of the core resources that I prepared for this session and that you should use and you should explore and you should click. I would like you to engage with this observable notebook, and not only by clicking the video and watching the video and exploring the resources, but also, if you want, by playing with it. Because in a moment, the second thing I wanted to say is this, that this is an interactive notebook and you can locally modify it. So this is the first resource that you should have, is this observable notebook, but you should also have a Python notebook that it contains all the code that we will use to explore and analyze the relationship in the data that we will gather from the net, and that we will also use to export the data file that we will need later to create these interactive networks. So two things: this notebook and a Python notebook that you should have at this moment. The second thing that I wanted to say is that I would like to briefly introduce this environment I'm using at this moment for this specific resource. This is Observable Notebooks, and maybe some of you are familiar with it. In case you are not, this is a really useful environment because it allows you to create notebooks that are similar to Jupyter Notebook, but in this case, it is running on your browser. It is using JavaScript, and it allows you to create interactive visualizations. It allows you to combine it with text, with videos, with images, all together, and it allows you to publish it to the net and to make it available publicly from anyone. I really encourage you to play with it. I think it's a really powerful tool, and to be honest, to prepare this class, I've been playing with it a bit, that I haven't done it for quite a while, and there are like new improvements, and it is just all the time getting better and better. So let's start. Let's start by something that I'm pretty sure that you know perfectly at this moment, but I would like to stress why we use networks. And this is something that I include here because I would like to stress it because for me it's important. And the first thing to say is that we are using networks when we are mapping relationships. And relationships is really the key when we are talking about networks, because they show relationships among a lot of things. I mean, really in general. So we can be talking about relationships between different entities, and these entities can be humans, can be authors, can be artists, plants, ants, can be proteins, can be anything. The thing is that we have all these entities, and any relationship that can exist between these entities can be mapped in a network. And when doing that, we are creating a way in which allows us to map all these relationships and allows us to understand the complexity that there is behind this specific system or community that we are mapping. So as I was saying, we can map relationship between humans, and this can mean that we can connect to humans that because they have a friendship, or because they co-author a book together, or maybe because they are somehow connected because they have some acquaintance, or because they're a pupil and a student, But we can also map, we can also visualize entities that actually are not humans. As for instance, we can be talking between animals and plants, but we can also talk, we can also visualize protein-protein interactions, and we can be also making visualization about the relationships that exist in nuclear physics interactions, for instance. So anything that is a relationship can be visualized. And this is relevant, and I would like to state the second point is that networks is a really efficient and powerful way to visualize and to deal with complexity. And really, networks is this really a strong tool to map all this complexity that we sometimes and really often and probably more often than we would like, we found in different systems. And this is something that actually social scientists, sociologists, they know from long ago, also physicists, also mathematicians, but little by little, you know, in other disciplines, in society and in science, networks are being used more and more in order to map all this complexity. I would like to give you really fast an example. We are now in a moment of peculiar in the sense that every time more we are facing really complex challenges. We're facing climate change, we're facing the enormous food waste that we produce, we're facing the bioplastics, the microplastics challenge, and tackling these challenges imply actually having a good understanding which are the actors that are open to tackle these different challenges. And if we want really to engage all these actors, and we want really to understand what is the complexity behind these challenges and how to tackle them, we necessarily need to map this reality. And in order to map this reality, there is a practice which is called system mapping, which actually what they are doing is create these networks of actors, networks of constraints, networks of roles all together. And when all of these complexities map, then we can start moving the different actors and we can start implementing initiative that actually can mobilize the different actors in this network that now, thanks to that we map it, we can understand it, and we can open up opportunities to make changes in these systems. And this is key. And with that, I want to say that networks are a really useful tool to map complexity, and mapping complexity is fundamental, for instance, if you want to tackle challenges, but also if you want to scientifically understand reality, for instance. And this is key. In this sense, in this sense of mapping complexity and relationship, these two ideas that I want to stress in this point, I'm sharing with you this video, which personally I like it a lot. It was published by Nature in 2016, and it comes from an article from Martino and Gao. And what they're doing here is that actually they are mapping the relationship between animals and plants in different ecosystems around the world. And then they are analyzing the stability of these different ecosystems by deleting little by little the nodes, by deleting plants or deleting animals of these ecosystems, and they see at which point the ecosystem is not anymore stable. It breaks. And this is fundamental to understand what is going on with the biodiversity loss in our planet, and to understand at to which point ecosystems can be stable and at which point they will break, because the biodiversity loss reach a point up to which the ecosystem cannot continue functioning as it did before. And this is again about mapping a lot of complexity and also using network science to study the properties of these networks and being able to derive really important information about the complex world and it and their relationships. So in this sense, I really invite you to watch this video, Network Earth. It's really interesting, and also I think it presents really these two notions that I want to stress here today. So now let's talk about a bit the properties and let's present some examples, good examples in my opinion, about interactive networks. So I will base this section in Ognanova, okay, in this tutorial published in 2019 on how to build networks using R. And if you're using R, actually, I recommend you quite a lot this specific tutorial. So Ognanova arcs, the networks can be used to, as I was saying, show links between entities, so relationships again, but also when we connect to nodes with a link, or also its name as an edge, and this edge can, the strengths of these links can be also mapped by, for instance, visualizing the thickness of this link can be used to map the relevance of this relationship between these two entities. And then for instance, we built these networks in which we connected all these different nodes and these different edges. And when they are all connected, this network actually is depicting a shape. And this shape actually is showing us the structural patterns and properties of this network. And this is something that is really important of networks. They allow us to understand what is called the topology of the network. So that is the structure, the patterns that the different nodes, when they are connected, are drawing, or the shape that they produce when they are all connected. And finally, network can also be used to depict those entities that are more connected than others. And with this, I mean that actually we can use, for instance, we can analyze the edges, that those nodes that have more edges that are connected to that specific node, and we can see those nodes that are more relevant to the network. And we can also detect communities. And in these communities, we can see those nodes that they tend to be more connected. For instance, could be those authors in a network of co-authorship that actually tend to collaborate more among them. So before continuing, I would like also to comment this chart that now we are seeing, in which we can see the different components that we can use to code information in a network. We can use, for instance, the color of the nodes. This color of the nodes can be used, for instance, to show a specific property of these nodes, and in a minute I will show you an example of this. But also it can be used to codify the community to which the node appertains. That is, all those nodes that they have the same color, it means that they tend to be more related between them in the network. Then the position, as I said before, when we place all the nodes in a network, the position that they have, this position gives a lot of information, because the position that they have is depicting the patterns that these nodes have. So the position is giving a lot of information. It's giving us information about the topology, about the structure, about this network, and this is really important. Then we can also use the size. We can modify the size of the nodes. We can make size, for instance, we can make those the example that we were talking in the network, for instance, in the ecosystem, for instance, in the node in the ecosystem are one of the species. The number of species that there is in this ecosystem, for instance, can be the size of the node. And for instance, if two species have a stronger codependence, this can imply that the thickness of the edge that is connection to these two species actually will be more thick. We have seen, though, both the thickness of the edge and the size of the node. And finally, another way of also codifying information is using the shape. We can use different shapes for the different nodes, and we can also use different shapes for different types of links between nodes. And I will also provide an example for both the size and the shape for the four examples that I selected for this class. And also we can also use arrows and labels to provide even additional information to the network. Okay, so have it in mind, color, position, size, and shape are those four components that we can use to codify information in a network. So let's explore 4 examples, and these 4 examples are categorized by 4 ways in which a network can be understood, or 4 goals of networks. The first one is networks as a mechanism to map evolution. Another one can be networks as a mechanism to map relationships. Another one can be maps as a storytelling resource. And finally, simply, networks as art. So let's start with the first one, which is mapping evolution. I would like to show you this example, which is this example concretely has been created by this guy who's called Noil. I really invite you to check his website. You have it here, the link in this description, because there are a lot of networks and actually are really fascinating, some of them, if you're interested in philosophy. But coming back to this example, this network is based on Collins' book, which is called The Sociology of Philosophy. The network is visualizing 440 years of relationship between philosophers. Okay, so we can see that the years little by little are actually going forward in time because we're before Christ, so the numbers are decreasing, but actually it means that we are going in direction to the future. And here Collins is actually using, not sorry, Collins no, the author of the network is using the node of the colors to codify an important information that Randall Collins is specifying in his book Sociology of Philosophies. Let me repeat again that in Sociology of Philosophies, it is explained the different kinds of relationship that the different philosophers in ancient Greeks they had between them. So what we are seeing here is this social network actually of ancient philosophers in the ancient Greece. So in this network, if the node is light green, it means that the relationship if the edge is light green, it means that the relationship between the philosophers, it implies that it was master-pupil relationship. If the edge is dark green, it means that they know each other, they were mere acquaintances. If the edge is orange, it means that there is a conflicting relationship. So they had some sort of, they did not really agree on each other philosophical standpoints. And finally, if the color of the edge is light blue, it means that the relationship is only suspected by the author of the book, in this case, Sociology of Philosophies, Randall Collins. So I invite you to read a bit more description. And as I was saying, I really invite you also to check the website of Noel, the person that actually built this network, because it's really interesting and there are other examples about networks related to philosophy. Now, let's explore an example about mapping relationships. This example is actually new because this is not the first one that this session is the third year that we do this session, and this is a new one that I included this year, and I found it nice. I found it a kind of simple but beautiful example. This comes from the MoMA, from the Contemporary Art Museum in New York, and actually what we're seeing here is they are mapping what they called Inventing Abstraction 1925. This is an exhibition from MoMA in 2012, and what they were explaining here is what are the relationships, how really abstraction in art was created, and of course, as most human ideas, they were created after a lot of interaction between different humans, in this case artists. So in this network, two artists are connected if they are acquaintance of each other. And as we can see, for instance, in this sense, we can see that Tristan Tzara, but also Francis Picabia or Leger are really important networks in this, really important nodes. They were relevant artists in the period in order to habilitate this process of inventing this abstraction, of creating this new way of understanding this new current within the history of art. So as I was saying, the names that, I mean, in line with what I am saying, the names that are in red are those artists that are more relevantly connected to the community in which they appertain to. So again, let me emphasize again this point. Pablo Picasso is in red because it was a relevant artist with the people that they had around, because it connected a lot of artists. It had a strong contribution to his network. So this network is a part of being really beautiful, is interesting because here we are codifying those networks. Here they are codifying something which is important to them. Identify those artists which are more important. And something that I like also for this network is that we can drill down to a specific network by clicking to one of these something I think is going wrong. By clicking any of these networks, for instance, I click now Kandinsky, I can see also the network that actually Kandinsky built around him and influenced him, but also he influenced all these artists to create this avant-garde movement. So again, I really invite you to explore this network, because personally I found it really beautiful, and also of course the content is really nice, because for each of these different artists you can also explore the art creations that are now exhibited in MoMA. The last two types. The next one that I wanted to show you, this goal of networks, or how networks can be actually used, is through this storytelling, telling a story. And I would like to talk about this example from Simler. Okay, he created this example, which I found it, again, this is a really beautiful example. This is also a new example from this year, and in this case, Simler, which actually is a researcher, he's talking about the concept of diffusion in networks. And he says that networks are really important. Actually, I quoted the text that we see here, that we are seeing right now. I quoted in the Jupyter, in the Observable notebook, because I think he's making like a strong statement defending the networks, and I really like it, because I agree with him. I think networks are really important, and here he's using networks in order to depict this concept of diffusion, no? And he talked like what is diffusion, and he explained it like really precisely, and he explains how diffusion is relevant in infectious diseases. And I also included this example because, we are all affected by the COVID-19 pandemic, so this is something that is quite close to us at this moment. But also how memes are spreading in social networks, but also how wildfire is spreading in a forest, and so on and so forth. So in this specific example, Simler is showing to us, first of all, some theory about networks, but then if we scroll a bit, then we will have several examples that we can play with them about different diffusion models, or for instance, what happens when we include some sort of spontaneous activation, but also what happens when in our ecosystem there is immunity. And we can play with the different parameters of the networks, and we can play with different thresholds of immunity and transmission rate, and we can see how diffusion changes from case to case in this lattice that actually is representing nothing else than a network. So if you have some minutes, because actually it's a bit long, but it's really interesting, I really encourage you to read the whole article and see here how a network, even if you don't see the edges, but this is here used as a network, and this is also interesting, because when we're talking in a network, networks have lots of different shapes, and sometimes we won't see them as the way as we imagine and as we canonically represent them, but networks can be represented and exist in a lot of different forms. And finally, the last example that I wanted to show you. This is one of really my completely favorites. This comes from Nadia Bremer, which is one of the queens of data visualization. I also invite you, if you like data visualization, I invite you to check her webpage. I included here in her name. And in this specific example that I included here, what we see is really, she's trying to map a lot of information. We are seeing here cultural heritage. So we are seeing like, and with cultural heritage, I mean now it comes to my mind Castellers in Catalonia, no? I mean, cultural heritage could be material and immaterial. Here is they are both concepts, and in this network, she was working on because the United Nations asked her to make this representation. She wanted to visualize all this complexity, and I'm showing this example to you because I think it's a fascinating example on how to deal with an enormous complexity and actually how to succeed to do that. The best way to understand this network is by accessing this pop-up, and as you can see, we're visualizing this intangible cultural heritage. And the first thing that we see here is that the nodes that are field cycles, so field nodes, are actually represent cultural heritage. Then the cycles that contain some text within, or the stroked cycles, as she says here, they represent concepts. Can be dance, can be materials, can be wedding, can be, for instance, handcraft, can be wood, so it can be materials, it can be different types of cultural heritage, and so on and so forth. So there are like, not only we are seeing different types of nodes, but also we see different types of concepts. So again, this notion of a lot of complexity. The bigger the concept, the more connections it has connected to it. Then look at this, something that I really like. We are using here something that we said before. We are using different colors, but we are also using different shapes, because here we see cycles for concepts of intangible cultural heritage, but we also see different shapes to codify a country and a region. A country is codified by using a rhombus, and the region is codified by using an hexagon. Then, again, we can also use colors, and we can also use the physical position of the nodes. So position and color here are used to identify those nodes that tend to be more related between them. So they are used to codify the community in which they appertain. So now we are using color, we are using position, but we are using shape to codify all this information, and size also we are using it to see those concepts that are actually more connected. And what we mean is the links. And we use the links to connect all these different cultural heritage, this concept, these countries, these regions, to connect between them so we can explore them. And those edges that actually are more, the thickness and the opacity is higher, it means that they are more relevant, as she calls them, primary connections. And those nodes that are, those edges that are less relevant, she calls them secondary connections. Okay, so opacity here and thickness are used to codify also the relevance of the edges. I leave it here for you to explore it. It's really interesting, especially if you're interested in cultural heritage. It's really a beautiful example. Okay, so now enough of theory. Let's start with the practical side. In this session, as I was saying, the aim here is to create a network. In this recorded part, what I want to do is to explain to you how to use Python and how to use an API, in this case, using an online resource in order to obtain some data, analyze this data, identify the different relationships in this data, and then export a file that then we can upload in our observable notebook, and it can be used to create a network. I'm repeating this because I really want you to understand this whole process and to have it in mind and understand each of the steps by little we are covering. So which are the requirements? You have to be comfortable with Python, Pandas, with Jupyter notebooks. It's really recommended if you have some understanding of JavaScript, and if you have some knowledge of D3s, that is spectacular, but of course I do not expect that you know some D3. It is a good practice if you have a GitHub account, because observable notebooks are connected with GitHub and it makes your life easier. But actually, this was more mandatory because I did it different in other sessions. Here is more a recommendation, actually, that something that is actually mandatory. So as I was saying, this first part, which is 1 hour, split into parts of half an hour and half an hour. Now we're going to fetch the data and process the data in Python. And the second part, which is the one that will be in vivo, is the one that we will build the network using D3 and Observable. So let's build it, but what are we going to build? What we're going to build is something which is similar to MoMA's inventing abstraction, 1910-1925. So we want to map relationships. And what we will do specifically is we will identify co-authorship patterns of a given musician, the one that you like most. I choose, for instance, John Coltrane, the jazz musician, but you can choose whatever musician you prefer. And we will see the co-authorship patterns in their musical recordings. So let me explain what I mean with co-authorship patterns in musical recordings. Conceptually, what we will be doing is gather all the albums that one author actually published during his lifetime, and taking all of them, we will take each of the authors, each of the musicians that actually participated in the recording or in the creation of these albums, and we will see how they are connected between them. So, for instance, in one album we have A and B, and in the next one we have B and C, then of course B will be connected in these two albums. But in order to be clear, when we talk about co-authorship, I mean two things. The first one is the intuitive collaboration in music. This means that they both collaborated. Like, for instance, I included here this example of Zetangana and Rosalía and Antes de Morirme, no? They both published this song, and in this song they both collaborated to create it. But there is another way to understand co-authorship, and it means that, for instance, an artist, this artist created some song, and then a band recorded pieces of the music of this composer, and they acknowledge this composer by including its names on the album. What happens is that this is really common, for instance, if we work with a classic composer, like for instance, Mozart. What happens is that Mozart has been recorded hundreds, thousands of times, probably tens of thousands of times has been recorded. So what happens is that actually Mozart does not appear, has not been recording his own music in all these recordings, but what happens is that actually the musicians are acknowledging that this music was composed by Mozart by including him in the as one of the authors of the album. And this is what we will see, and this is something that we should take into account in order to interpret correctly the networks that we will build. So I would like you to enjoy this process. So I would like to ask you to choose one musician that you really like a lot, but you have taken into account that this musician is someone that tends to collaborate. For instance, songwriters do not work because songwriters work alone. They do some collaboration from time to time, but in general they tend to work quite a lot, so they are like solitary musics. So this is not a good kind of musicians to use. So I really encourage you to use some musicians that actually have lots of collaborators, that he made a lot of recordings during his life and before dying, if he's dead, of course, or she's dead, and that is better if she had a long career, or especially if it was a fruitful one. So really fast, last one final point. We need to get all this data. Where we do get all this data about all these artists? We will be using this tool, this platform, which is called MusicBrainz. MusicBrainz is a huge repository of collaboration in music. Okay, so it's a sort of music database. There is a lot of information of music from all periods, and it's a really powerful tool that we will be using, because one of the advantages of MusicBrainz is that actually it has an open API. And for those who doesn't know what is an API is simply a program that we can use by asking specific parameters. This program can give some information that is stored in a database. So we will be using the MusicBrainz API actually to provide all the information that we need to build this network. We will ask to this API all the data that we need to map the relationships that are in the albums of the musician that we want to know more. So here you have all the information. I invite you to read all the details of how this works. But to put it simply, for instance, I'm accessing here the 100 first albums as they appear in the database. This is not in chronological order of Wolfram Amadeus Mozart. We are seeing here like 100. For instance, this one, I see now the Mozart Piano Sonatas Volume 4. Okay, so I'm asking to the API actually to give the first 100 albums that it has stored in its database that actually Mozart has authored. And again, let's remember, not authored, was not playing there the violin, but actually it was the composer, and it was acknowledged by the musicians that actually performed his music. So we will use this recursively, asking 100 albums by 100 albums to obtain all the albums that we want to analyze, because we want to obtain all the albums, and when we have all the albums, we are able to build all this network of co-authorship. So co-musicianship, I don't know. In my case, as I said before, I want to analyze the network of John Coltrane. Okay, in order to do that, I'm going to explain you how you can get this code, the MusicBrainz ID. This is key, okay, because the MusicBrainz ID is the identifier that is a unique identifier that the database is using to identify, in this case, a musician. And if you have this MB ID, then you can use it in the Python code that I will show later to obtain all the information needed to construct the network of this specific musician. So let's search for the one of John Coltrane. So I actually have it here. Before going further, when you have all the results that actually are matching the name that you search, I really recommend you to be sure that the person that appears is the one that you're interested. And one way of verifying this, in my case, is, for instance, I know that John Coltrane was born in 1926 and he was dead in 1967. So there are really good chances actually that this is the John Coltrane that I am interested on. So here we have it. We have the information of John Coltrane, just saxophonist. Now I see that there are even higher chances. And this part of the URL actually is the MusicBrainz ID that I'm interested. Okay, so the key thing that you should keep from this first part is that search in MusicBrainz the musician that you're interested on, and find this MusicBrainz ID. And when you have it, store it well, because we will use it then to ask to MusicBrainz API all the information of all the albums of this artist, and with this data then we will be able to build this network of co-authorship in these albums. So I will stop here this first part of this first part, and in the second part we will be using this MVID to fetch this data, explore this data, analyze the relationship, and export a data file that we can use later for visualizing this interactively. So thank you for your attention, and I see you in the next half an hour video.